So what we are working on in this chapter is inequalities, and a lot of our theorems are going to be called inequality theorems. So to begin with, if we have two numbers, such as A and B, then one of these things has to be true. Either A has to equal B, or A has to be greater than B, or A has to be less than B. We've been working mainly with this property right here, A equals B. So we are going to be working with inequalities this chapter, and we're going to start out with the properties of inequality. So what you see on the top of page 204 are your properties of inequality. And in some ways it parallels to our properties of equality. For example, if you have two inequalities, A is greater than B, and C is either greater than or equal to D. That means C's value could be equal to D's value, or C's value could be larger than D's value. Then if I add C and D to both sides of the first inequality, adding the larger values and the smaller values, what is the symbol that should go in between these two expressions? Greater than, yes. The reason why not equal to is even if C equals D, because A is larger, then if I add A and C, I will still get something larger than B plus C. So in a way, this could be said to be the addition property of inequality. Meaning you can add the same values to both sides of the inequality and you still have the same direction to your inequality. It's still greater than. Our next property is a multiplication or division property of equality, and this property has to be split into two pieces. The two pieces really have to do with whether you're multiplying by a positive number or if you're multiplying by a negative number. So you start out if A is greater than B and C is positive. When you say something's greater than 0, that means it's positive. Then if you multiply that positive number times both sides of your inequality, it will remain the same. So then A times C will be greater than B times C. The same thing if you divide both sides by that inequality or by this positive number C. The reason why it's different if C is negative is what happens on the number line when you go to negative numbers versus positive numbers. So for example, I know that 5 is greater than 3. But if I change their signs and I work with a negative 5 and a negative 3, now which one is the larger? Negative 3 is the larger. You see how if you change the signs, then it will change that direction of the inequality. That's supposed to be a rotate arrow there. Okay? So if you multiply by a negative number, you have to change the direction of the inequality. So the second piece to this multiplication division property of equality, we have a piece 1 and then a piece 2, is going to be if A is greater than B, but C is negative, then when you multiply by that negative number on both sides, you must change the direction of the inequality. So then A times C will be less than B times C, or A divided by C is less than B divided by C. If you multiply or divide by a negative number, you must change the direction of the inequality.
What if B were negative, like A was negative, B negative 3, and we multiply by negative A?
It still changes the direction because, for example, negative 2, negative 3, I know that negative 2 is greater than negative 3. But when I multiply by a negative number, so multiply both sides by a negative 3 or whatever negative number, and what we end up with is a positive 6 and a positive 9, but which one is greater? The 9. So you see that that direction of the inequality is switched yet. Now, our third property of inequality is a type of transitive property of inequality, which means we're comparing two inequalities with the same number in both of them. So it starts out with if A is greater than B and B is greater than C, then, and what do you think we're going to be able to say? The larger one, since it is bigger than B, which is bigger than C, must be greater than that smallest one. So your first one, A, must be larger than C. And that's a type of transitive property of inequality. Our last property of inequality doesn't have much of a name. We're just going to call it the last property. And all of these will be properties of inequalities. You can use them in proofs or things like that. If you use this one, you can refer to the last property of inequality. So what it says is if you have a sum of numbers, if A plus B is greater than or equal to C, let me go with this one. If A equals B plus C. That's the way it starts. And C is positive. So if that's the case, then A must be larger than B. So if A equals B plus a positive number, then A is actually to the right of B on the number line. So A must be greater than B. Nick, when you do that, you're not only distracting Branson, but you're distracting probably whoever is watching, including me. Okay. So let me talk about this a little bit. If x equals negative 3 plus 2, what's the value of x? Negative 1. So I could say negative 1 equals negative 3 plus 2. And isn't negative 1 going to be larger than negative 3? Yes, because it's the sum of negative 3 and 2, right? Negative 1 is greater than negative 3. That's what this last property is saying. If a number is a sum of two numbers where one of those numbers is positive, that C is positive, then that number is larger than the first number there. Or if they're both positive, if B and C are both positive, then A must be larger than either one of them. We have one theorem in this section, and we're going to use mainly this last property in proving that theorem. And it's called the exterior angle inequality theorem. So theorem 6.1, I'm going to move all this over so I have a little room. what the exterior angle inequality theorem says is the measure of an exterior angle of a triangle is greater than the measures of either remote interior angle. Yeah.
What I just told you earlier is now finalized on how we do the next week.
Okay. Thanks, Angelica.
Is this one?
What was that?
Okay, is this one?
204.
Now, where this whole idea comes from is Theorem 312. Theorem 312 tells us that when we have a triangle and we extend one of the sides, the angle that is formed right there is equal to the sum of the two remote interior angles. So it's equal to the measure of 1 plus 2. Here, our given can be just the diagram, really. We have an exterior angle. And what we want to prove is that angle 3 is greater than angle 2 and angle 3 is greater than angle 1. By Theorem 312, which is your exterior angle theorem, since measure of angle 3 is the sum of those two angles,
Would it be the last?
it is perfect, yes. Since measure of angle 3 is the sum of those two angles, then we know the angle 3 has to be larger than either one of them by the last property of inequality. End of proof. Yes. All right, we're going to do some examples, so I'll stop this here.